Hey guys, so I'm here today for our first lesson, which is about limits. And today we're going to talk about limits from the graphical side of things. So what do we see when we look at a graph? Okay, here's kind of our big question for this chapter. Everything in calculus is going to come back to a limit. So before we kind of go on, I want to fully explain what a limit is and what it means. So the big question that a limit answers is this, is what does it mean? What does it mean to get infinitely close to something? Infinitely close to something. And at this point, I should probably step back and apologize for my terrible handwriting. It's just kind of a skill you're going to have to deal with for this year, but it's really just going to prepare you well for college if you have this experience with someone who's as bad at writing as I am. So anyway, here's the notation that we use for limit. So we write it like this. We write the word lim. X approaches some number with an arrow, like X arrows a number under it, of f of x. And the way you read this is as the limit as x goes to 0 of f of x. So what this means, as x gets really close, and by really, of course, we mean infinitely close, as x gets really close to 0, what number, or what does the value of f of x approach? And of course, when we're thinking about this value of f of x, that of course means the height of the graph. What is the height of the graph going towards as x, the horizontal component, goes to 0? Okay, so let's take a look at this. I've drawn an example here of some other function g of x. So suppose I ask you, what is the limit as x approaches 2 of g of x? So again, that's really just saying, as x gets closer and closer to 2, what is the height of the function g approaches? Okay, now I'll do x goes to 3. That actually makes more sense given my terrible drawing. Okay, so take a look at that. So as x goes to 3, what's happening on our graph? Well, we're going towards this point right here. So as x goes to 3, the height approaches 3. It gets infinitely close to 3 as we get closer and closer. So we write that our answer there is 3. Okay, and we'll do a couple more. What if we take the limit as x goes to 0 of this function g of x? Well, as x approaches 0, we get closer and closer to that height of 1. If we took the limit, say, as x approached negative 2 of this function. So that's saying as we get closer and closer here to this point where x is negative 2, we see that limit is going towards a height of 0. So that's how we would kind of interpret these right there. Okay, so that's the basics of graphical limits. So let's start talking about kind of some weird cases. So let's look at an example where we have a hole. So I'm going to draw another function here, f of x. And this function is going to look very similar to a parabola, except it has a hole at the point right there at 0. And then at that point, we're going to have a value there of 4. So of course, what that means is that this is the actual value of f of 0. f of 0 is equal to 4. Okay, but for everything close to 0 and everything except 0, it's going along this parabola curve. So the question we have, of course, is what is the limit as x approaches 0 of f of x? Okay. So let's think back to the definition that we talked about at the beginning of the class. So as x goes to 0, we ask, what does the height approach? Now, if you think carefully about this, does it matter what the actual value of f is at that point? No, it's just saying, as we approach the point, as we get closer and closer to that point, what are we going towards? Well, we're going towards that hole where the function's undefined, and that hole has a height of negative 1. So even though the value of the function here is 4, the answer we're looking for the limit is going towards a height of negative 1. So that's kind of important, and that's how we have to think about this. So just think if the function were to just keep on doing its thing and just keep on following this path, what would it go towards? So that leads to one kind of big key is the actual value of f at the point does not affect the limit. Doesn't affect the limit. And that's one of the two kind of key points from today's lesson. Okay, so notice that here we'd have the same limit for these cases. So if you just like actually had the parabola, you would still have a limit of -1. If you had the parabola with an empty point and then you just like never filled in that, and then you never filled in that point, it would still have that exact same limit of -1. Okay, so that's important here. The next thing we want to talk about is something called a one-sided limit. So a one-sided limit is just saying like, what if you just approach from one side, either the left or the right? So what if you just approach from the left or the right? Okay, and thinking about like, just the number line, the positive side is the right side, the negative side is the left side. So if I ask you, for instance, to answer some questions about this graph, so I'm going to draw just another graph here. And let's say we have, here's 5, here's 10, here's 15, and then we'll just do the standard scale on the y-axis or whatever. So as we approach the point 2, 3, okay. As you approach the point 5, we kind of go up with a straight line towards that point. And then at that point, we're going to jump down to 1 and then go across there, just a straight horizontal line to 15. And then after that, let's say at 15 on the right side, I don't know, like we just go down, it doesn't really matter. Okay, and that happens, it looks like a -4. So when I ask you to find, for instance, the limit as we approach 5 from the negative side, I write it like this. So the limit as x approaches 5, where we'd write an exponent, we just put a little negative sign there. So that exponent means the left side, the negative side. Okay, so what this is saying is, again, what happens to the height of f as we approach 5 from the left? So we approach 5 from the left. Well, hopefully that's pretty obvious looking at this function. As we approach 5 from the left, it's going towards a height of 3. Again, it doesn't matter that the real value is there. We're going towards that value there of 3. Okay. Now, on the other hand, if we were to take the limit as we approach 5 from the plus side, again, we'll put a plus where you put an exponent. So the limit as x goes to 5 of fx, from the right side, it's going towards a height of 1. So we'll write that limit is 1. And that's kind of what the question would ask you. Okay. So from a similar perspective, of course, if we ask for the limit as x goes to 15 from the negative side, of course, that's still going towards a height of 1. If I ask you for the limit as x goes 15 from the positive side, it looks like it went down 1, 2, 3, 4. It looks like it has a height on the right side of -4. Okay, now what if I just pick a point in the middle, right? What if I pick, I don't know, like 8? So what if I take like the limit as x goes to 8 from the positive side of f of x? And what if you take the limit as x goes to 8 from the negative side of f of x? Well, like nothing interesting is happening there, right? 8 is kind of in the middle of our graph. So as we approach it from both sides, it's going towards the same height. It still has a height of 1 in both cases, so nothing crazy is happening there. Okay, so that's what's going on with one-sided limits. I think like one thing you're probably asking here is, well, okay, let's look back at what's going on at 5, right? And what we see at 5 is the left-hand limit is 3 and the right-hand limit is 1. But what if I ask for the overall limit? So if I ask for the overall limit as x approaches 5 of f of x. So if I just ask for like limit x goes to 5 with no sides on it from f of x, well, in this case, you just need to consider both sides. Okay. So what is the value as we get closer to 5? What is the value of the function approaching from both sides? Well, is it approaching one single value? I mean, you might think, okay, well, it's 1 on one side, it's 3, so maybe it's 1 and 3. You might think we're going to average them. Maybe you think it matters where the function is, even though we just told you it doesn't matter what the actual value of the function is. Okay, so what we're going to say in this point is that this limit as x goes to 5, though, doesn't exist. And the reason being that it's different on both sides, right? On the left, it's going to 3. On the right, it's going to 1. So we say that this limit equals DNE, and that stands for does not exist. Okay, and that gives us to our second kind of key point of today's lesson, is that for a limit to exist, it must be the same on both sides. It must be the same from both sides. And when someone asks you to consider a limit, you should really be considering what's happening on both sides, whether that's a piecewise function, a graph, something like that. So you must have that limit as x goes to 5 from the negative side of f of x has to equal the limit as x goes to 5 from the positive side of f of x. And that's true for any kind of limit you're thinking about. It's got to match on both sides. Okay. Obviously, the real value doesn't matter. We just care about what happens on both sides. Okay, cool. So that's the idea of what's happening. And just with some other cases, like obviously if I asked for the overall limit at 8, that would still be 1. And at 15, we would also see it doesn't exist there because it's different on both sides. Okay, so you might ask, like, what are some of the other ways a limit might not exist? So ways a limit doesn't exist. Okay, so we could have what's called a jump, and that's what these cases are, where it kind of jumps from one side to the other side. You could have an asymptote. So in the case of an asymptote, what that would look like is, say you had like a graph like 1 over x. If you ask for like this limit at 0, it doesn't exist, right? It's going to positive infinity on one side, it's going to negative infinity on the other side. Okay, and the other case is if you have something really weird. So something really weird is, for example, like sine of 1 over x at 0. And this isn't something that's like going to come up too often, but let me just show you a graph of what it looks like, because I think it's pretty sick. Okay, so we're going to go to Desmos, and I'm going to graph this function for you, and I think you'll see something like pretty awesome happens. So let's put in a trig function, sine of 1 divided by x. Okay, so this is what the graph looks like, and we're asking, like, what happens at 0? Well, look what happens when you zoom in, right? Like, it just keeps going up and down. So no matter how far you zoom in, it has this infinite number of oscillations, and it never settles down. Ooh, that's kind of sweet. Yeah, oh, cool, okay. So no matter how far you zoom in, it still like just keeps bouncing back and forth between heights and -1 and 1. It looks like it kind of broke Desmos. But you can see it's not approaching a limit, right? It just keeps going up and down and up and down in there. All right, I thought that was pretty sweet. Let's go back to our notes then. So one more thing you can be aware of is a limit could be a positive or a negative infinity. So that would be kind of the situation where you had an asymptote. So if I asked you, for instance, like maybe you had a graph which went up to positive infinity on the right and left side at 0. So in this case, your limit as x approaches 0 of this function, we would write that as infinity. And of course, if it was going down, we'd write it as negative infinity. Okay, so that was graphical limits. Hope that helps. Please, please, please let me know if you have any questions, and I'd love to help you understand any of this. I'll see you soon.